With Ehrenfest theorem proved, we're down now just to step number 3. We have to apply this now to x and p. So let's start with x, right? So if I want to know the time derivative of the average of x, of my packet, I'm hoping, this is what we have to prove in order to get to f equals ma. I'm hoping it's just what I would expect classically, that it's nothing other than the average momentum in my packet divided by the mass m. Now I don't know that that's what it is, right? What I do know from Ehrenfest theorem is that this will be the average of 1 over I h bar acting on the commutator between the x operator and the Hamiltonian operator. And if I want to write this out, more precisely, that is then where I take my current wave function, right? My current value of my wave function, and I take its inner product with this operator actually applied to my current wave function. So the big question then is, what is this quantity? So let's compute that and see if it gives us what we need to establish this first key Hamilton equation. So what is that? So that is defined to be, again, where I do the operators in the order that they're written, and I subtract off when I do the operators in the other order, like so. Now, I guess I can be even more explicit since it's the first time we're computing a commutator. And by the way, this is the way you compute commutators, right? These are just well-defined mathematical operations, and our job is to see if there's some kind of shortcut or simplification. So let's take a look here. So the first thing I'm supposed to do, if I look at this piece, is it says I apply my Hamiltonian to my wave function. Now we know what our Hamiltonian operator is, so that part's pretty easy. That's minus h bar squared on twice the mass, the second derivative with respect to position of my wave function, plus the potential, which depends on location x, times my wave function, right? This is exactly h hat acting on my wave function. When I apply the operator x to a function, all it does is it multiplies that function by x. Well, here's my function all worked out, so when I apply x hat, that just means multiply it by x. Okay, that one's not much of a problem. Next term. So in the next term, notice from the definition, first I apply x to psi, and I know what the result of x on psi is. That is just the function x, right, times my wave function psi, which also depends on x. So my job now is to subtract off the Hamiltonian applying to this function, not the Hamiltonian applying to psi, but the Hamiltonian applying to x times psi. Okay, I think I know how to do that. To apply the Hamiltonian to any function, I do minus h bar squared over 2m times then the second derivative of my function. My function that I'm applying it to is not psi, it's x times psi. So I better put x times psi of x here in my parentheses. And I'm making sure to write psi of x just to remind myself that it is actually a function of x because I will be taking some x derivatives. Technically, it's actually a function of x and time t, so I'll write the extra t in here just once. That, though, just kind of, becomes a pain in the neck for all that writing, so that's why I often will avoid it. But since this is the first time we're doing this, let's be very explicit. Now, that's not the end of the Hamiltonian acting on x times psi. The last piece is you add on the potential times whatever function you're acting on, which again is not psi, but x times psi. So I have x times psi. I can close my parentheses. This is then h acting on x psi being subtracted from x acting on h times psi. So we've translated all of our operator language now into straight mathematics. We should be able to look at this expression and hopefully begin to simplify it. So let's see what kind of simplifications we have. These derivative terms look a little complicated. Maybe we'll come back to those second. If I look at the potential terms, this is interesting. I've got x times v times psi. And here I've got v times x times psi. Exactly the same factors, just a different order. The other thing is, notice this comes as a plus x v psi, whereas this one comes as a minus vx psi. So it's the same factors, different order, and opposite signs. So I know this term cancels this term. Great. So now all that I have left are the terms that have to do with these derivatives. And since they have to do with those derivatives, I feel like maybe I should pull out some of my constant factors. So what I have here looks to be something like, I've got my minus h bar squared over twice the mass, right? Coming here from my first term. Then I have x times 2 derivatives with respect to x of psi. That's from this part. Then I have minus the minus. So I've pulled out the minus h bar squared on 2m, so that's still a net minus. And what I have now is 2 derivatives of x times psi. Okay. Well, that's some progress. That's a little bit simpler. It looks like what we really need to do then is to calculate this derivative and see what's left and whether we get some cancellations happening. Well, it's a second derivative, and we know a second derivative is always the first derivative of the first derivative. So now I have to take the first derivative of x times psi, but that would just be the product rule, right? That would be the partial derivative with respect to x of x times psi plus x times the partial derivative of psi. And of course, the partial derivative of x with respect to x is just 1. I guess I was being a little extra pedantic, but it doesn't help to go slowly. So now I have to take the first derivative of psi plus x times the first derivative of psi. No problem. When I do that, at first I'll get the first derivative with respect to x of psi from the first term. Now in this term, again notice I have to do the product rule. When I do the x derivative of x, that will just give me 1 times the derivative with respect to x of psi. So you'll notice the first term in the product rule for this second piece gives me exactly the first term that I had here. So this term is actually doubled. Plus then I have when the derivative acts on the second portion of my product, which will be x times 2x derivatives of psi. So we've taken the derivative. Now we can look at our expression for simplifications and notice, right, this whole term that I've been evaluating is subtracted off. So therefore, this x times 2 derivatives of psi is subtracted off from this x times 2 derivatives of psi. That's beautiful. This term cancels this term. The next thing to notice is there's a nice factor of 2 in the bottom and a factor of 2 on top. And finally, don't forget this overall minus sign that can hit this minus sign. So I'll have a plus and a plus. So the final result of the application of that commutator is there is a nice shortcut. For applying it, you multiply by h bar squared over m, and then you take the derivative with respect to psi. Perfect. So that then is my commutator. The final thing that I'm trying to compute, of course, is the time derivative of x with respect to time t. And Ehrenfest says that is the average of this commutator divided by IH bar. So I have to do IH bar, the commutator x h acting on, well, I'm going to make it a bracket. I think that's probably the safest way to do this. So this is my bra psi. This is the operator in Ehrenfest theorem acting on psi. And now you will notice that, okay, I have a factor of 1 over IH bar. And I've just figured out what this commutator does to psi. It's just this set of factors. So it's h bar squared over m. Oh, that's interesting. Times the x derivative of psi. And this gets even more interesting. Notice the 1 h bar in the numerator will cancel the h bar in the denominator. I have a factor of 1 over m I could pull out. And what's left inside is the inner product of psi with this magic combination, h bar divided by I times the first derivative of psi with respect to x. And now hopefully we're starting to recognize this. Here, just make it a little more neat so we can recognize it more easily. This h bar over I times the first derivative, that actually is the momentum operator. It just jumped out at us here. So I actually have then 1 over m times then the average momentum, because that's the momentum operator. That's exactly the definition of the average momentum. So we've proved the first piece of what we needed to prove F equals ma. The velocity of the packet is nothing other than the average momentum divided by the mass of the particle. Beautiful. So we've got one last thing left to prove. Finally, right, what we need to show is that we need the time derivative of the momentum to equal the average force, right? We're hoping that will give us the average force. Well, again, we were going to do this, so that's a question mark. We don't know if that's equal yet, but we're actually going to prove it using Ehrenfest theorem. So I will need the inner product of psi with 1 over I h bar, just writing down Ehrenfest theorem, times now the commutator now of the momentum with the Hamiltonian as applied to my wave function psi. So let's then compute the commutator. So we have to compute a momentum operator commuted with the Hamiltonian acting on the wave function. And again, we now know the procedure for this. You apply the momentum operator to h acting on psi, and then you subtract the Hamiltonian acting on the result of the momentum operator applied to the wave function psi. And we now know how to do these. Hamiltonian acting on psi, we just had that up above. That will be minus h bar squared on 2m times 2x derivatives of psi plus the potential v of x acting on psi. And of course, don't forget that psi is a function of x. I better just remind myself of that, right? And then that's the Hamiltonian acting on psi. I then have to apply the momentum operator, which has my factor of h bar on I, and it's an x derivative then of all of these terms. From this then, as you know, we have to subtract the Hamiltonian acting not on psi now, but on h bar over I times the first derivative of psi, because that's the momentum operator acting on psi. Okay, well, we know how to apply Hamiltonian to any function. Again, it's h bar squared on 2m times the second derivative of whatever my function is. In this case, my function is this slightly more complicated h bar on I times the first derivative of psi. And then to complete the Hamiltonian, of course, you have to add on what happens when the potential v of x multiplies whatever your function is, which again is this factor h bar on I times the x derivative of psi, and I can then close my bracket. So, once again, we've translated all of our operators into just straight mathematics. Now again, we look for simplifications. So one thing that looks kind of simple in a way is that here now I have two derivatives with respect to x of the first derivative of psi. That's just the triple derivative of psi with some factors. And here, the first derivative of the second derivative also just gives me the triple derivative of psi, once again with some factors. So there's some hope these might cancel out. Let's check out our factors. There's an h on I, and there's an h on I. There's a minus h bar squared on 2m and a minus h bar squared on 2m. So they have exactly the same factors. The only extra difference is that, well, this one comes with one net minus sign, whereas this term has two net minus signs. They come with opposite signs. They cancel perfectly. So this term and this term will cancel. Wow, that's nice. That's kind of a relief. The other two terms aren't too complicated, so they both have a factor of h bar on I. Here, I'll just write things down a little more neatly now. Then I have the x derivative of this product. Now that makes it a little interesting, doesn't it? v times psi of x. So I think I might get some derivatives of the potential in here now. Minus then v of x. And then there's again my h on I, which I factored out. And then that's multiplying the x derivative of my wave function. And then I can close my square bracket. Okay. Fine, fair enough. I think I know what to do, right? I just have to take this derivative and its product rule again. So that gives me the x derivative of my potential times my wave function plus then my potential v of x times the x derivative of my wave function. And, oh, this is nice. Notice this term that I just wrote down exactly matches my other term here. So these two terms will cancel. And now I have a very simple formula shortcut, actually, for applying this commutator on any function psi. What I do is I simply take h bar divided by I, and I take the spatial derivative of the potential, and I just multiply that number times my wave function. That is literally the shortcut, the application of this commutator p with h on my wave function psi. Okay, great. So now I have that one missing piece. I can finally compute the time derivative of my momentum. I now have to do the inner product of psi with 1 on IH bar times the result that I've just computed. So therefore, the time derivative of my momentum is equal to the inner product of psi with the 1 over IH bar that comes from Ehrenfest theorem times then the action of this commutator on psi. That action I just computed, that was h bar on I times the derivative with respect to x of my potential v of x, right? And that derivative only acts on the v of x applied to psi. Okay. Oh, perfect. The h bars cancel out nicely. I have two factors of I, which multiply to give me just a minus 1. So that's a minus sign. I guess I could put it in my bracket there. And then this is literally just the average of my derivative with respect to my potential. If I wanted to just, go back to the old school just to see it maybe a little more clearly, this is literally the same thing as the integral dx of psi star times minus dv dx, right, times psi. But psi star times psi, we know, is just the probability, p of x. So I'm going over all locations. I multiply at that location the probability density of finding a particle at that location. And finally, I multiply it by this quantity, the x derivative of the potential. But the minus of the x derivative of the potential is exactly the force, and this is nothing other than the calculation of the average force. So the time derivative then of the momentum, of the average momentum, is nothing other than the average force. And if you combine that with the fact that the time derivative of the position is nothing other than the average momentum divided by the mass, and you run through the first step of our proof, you can then finally prove and establish from some more fundamental underlying theory, Newton's law, the very famous F equals ma.